Okay, in this last segment, I want to talk about some applications of what we just finished talking about with molecules being glued to each other. And so the first example is going to be surface tension. And so take a look at that picture that is over there in the upper left-hand corner. And so you see that you're going to have some water molecules, so that each of the circles is now going to represent H2O. So I'll put 9 of them here. And then let's compare this water molecule here with this water molecule up here. So that this water molecule is being pulled in all of these different kinds of directions. So it's being pulled by all of the neighboring water molecules on it. Okay? But the one that is above it is only being pulled. So let's look at this one up here. So this one up here is only being pulled by this one over here, and then this one, and then this one, and then this one. So you notice that this water molecule is being pulled more preferentially because it's on the surface than this one that is down here. And so what this means is that these water molecules are going to be stronger up here than they are down here, and this is going to make a film at the surface. And so this is going to be called surface tension. And the picture that is on the top and over to this side shows a particular kind of bug, an insect, called a water strider. And as you can see, it is actually capable of walking on the water. And that's because of its mass is very small, and it doesn't cause enough force of gravity to be able to break the surface tension. So it can actually walk on the water. Now, don't do this, all right? But if you like torturing insects, you can take, if there's a bug that is on the water, and then you take a drop of detergent and you drop it onto the water, then all of a sudden that bug is going to go to the bottom of the water. So if you do this experiment, rescue the bug, get it out of the water. Don't be kind to animals, okay? But what that detergent does is it breaks surface tension. And then that's the reason why it's good for cleaning your clothes and your dishes, because it breaks surface tension. Okay, another one that I want you to take a look at is viscosity. And so you could take a glass of water and pour it out onto a table, and you would notice that it's very runny. And so the water is just going to make a nice, even thing on the surface. But then you could take maple syrup, very cold maple syrup, and pour that onto the table. And then what you're going to notice is that the maple syrup tends to do something like that. So it tends to mound up. And that's because it has a higher viscosity. The maple syrup atoms that makes it up are sticking to each other more than what the water molecules are. So viscosity has to do with how sticky like molecules are. So if you have a water molecule and a water molecule, they will stick together, and the how hard they stick together is going to be the viscosity. So that you can have things that have a large viscosity and things that are does not. So low viscosity, runny, high viscosity, whatever the opposite of runny is. So sticky. Who cares? Volcanoes. So have you ever noticed that you can have some volcanoes in Hawaii, and then when they erupt, the lava comes out and it just tends to go sideways, because that lava is not viscous. On the other hand, think about the lava that comes out of the volcanoes in the Pacific Northwest of North America. So that you got Mount Rainier, Mount Shasta, Mount St. Helens. And so what kind of volcanoes do they make? Those volcanoes tend to have a shape that looks kind of like that. And that's because as the lava comes out, it's very, very viscous. It runs very slowly, and it cools off, and it hardens, solidifies. So the kind of lava that comes out of the volcanoes in the Pacific Northwest of North America is different than the lava that comes out of Hawaii. And it all has to do with the viscosity of the atoms that are making up that lava. Okay, the third application is called capillary action. And so what this is it's how much a substance wants to stick to a different substance. So with viscosity, it was two identical substances. With capillary action, it's a substance and it's going to stick to another substance, like glass. So in this picture here, you have different kinds of tubes that have different thicknesses to them. And then it shows what happens when you pour water into each of the tubes. And you notice that the tube that is the thinnest, the water goes up the most because the water molecules are sticking to the glass, a different substance, and it's going up the tube. Another example of this is the picture that is right next to it, in which you've got pieces of paper. So you're going to you can do this experiment. So you're going to have a strip of paper and then take a black ink pen and then make a dot on it. Okay, then you're going to, you could just use regular alcohol for this. So if you have a dish and you put some alcohol in it, then take this piece of paper and dip it into the alcohol. So the alcohol is going to start to rise up the piece of paper due to the capillary action, and then it's going to carry with it the ink. And depending on which pigments are in the ink, the different colors are going to rise to different distances on the piece of paper. So we call this chromatography. And this is really important because we can separate different substances based on how they interact with the piece of paper. And so if you've ever seen a police drama where they are taking a sample of a chemical and they're having it analyzed, they do a very similar thing to this, where they take the chemical to be analyzed and they vaporize it, and then they send it through a chromatography apparatus that is going to separate out each of the different chemicals or compounds in the chemical, and then from that they can figure out what was that substance to begin with. Okay, so those are three examples of how in nature molecules being attracted to each other is important. So let's take a break, and when we come back, we're going to take a quiz over what you have learned.